Acha, we had looked into this continuous cooling curve and the isothermal temperature time transformation diagrams, and we have looked into this example of isothermal transformation paths for different microstructures. We have also looked into these heat treatments. Now, this is basically continuous cooling transformation diagrams or CCT diagrams. As I had mentioned, in these diagrams, the curve shape changes a bit, and then you have two kinds of cooling curves that are shown to you. The red line basically marks the start of the formation of perlite, and the green line basically marks the end of the transformation of perlite. If you are following through this blue curve, which is slow cooling curve, or in other words, you are having an annealing heat treatment, you would eventually get coarse perlite. But in case you are following through a relatively faster cooling rate, moderately rapid cooling rate, you are basically going through the heat treatment which is known as normalizing, and the structure that you would get would be fine perlite. In annealing, if you remember, you cool the sample in furnace by turning off the furnace, and in normalizing, you cool the sample in air by taking the sample out of the furnace. Now, these are the two cooling rates. This line basically marks the critical cooling rate, the point that touches the start of perlite formation uh, line. So, a cooling rate which is less than this cooling rate would essentially give you which structure?
Sir,
It
martin
would
side
give you
structure.
it would give you martensite. So if you look at the bottom, any cooling rate that falls in this category would essentially give you martensite. Any structure that forms between these two lines would give you martensite plus perlite, because let's say if I have this cooling rate, now the perlite formation started at this point, but since the line was not able to cut through the green line, perlite formation has not finished. So there is some quantity of perlite that would have formed, and the rest of it would have been converted into martensite. And if the cooling rate is slower than this, you would have essentially formation of perlite in those cooling rates. Now, if we look at annealing heat treatment on an isothermal or on a continuous cooling transformation diagram, you would see that if you have a slow cooling rate, slow cooling, you would essentially have the annealing heat treatment. In case you quench your material, which is very fast cooling, and quenching essentially means that you don't cut this green line, you fall something short of this cooling line, you would essentially have the structure or the heat treatment which is known as quenching. So annealing and quenching is clear to you. If you need to have tempered martensite or tempered heat treatment, essentially what you do is that you first quench your sample as shown in cycle B, and then you reheat your material to a lower temperature, let's say somewhere around to 60 degrees centigrade for some duration of time, and then you cool it back. So reheating the quenched sample for some time at a lower temperature gives you essentially the tempered heat treatment or tempered martensite. Now we will be looking into the properties of various phases that we have studied so far. Tempering or tempered martensite, it is done basically to reduce the brittleness of material. Martensite essentially is very hard and brittle. So in order to reduce its brittleness or hardness to some extent, and to reduce the internal stresses caused by quenching, you basically do the tempering heat treatment. Tempering temperatures could be various, 200, 400, 600, any temperatures in between. And if you see the tensile strength and yield strength variation with regards to the tempering temperature, you would realize that as the tempering temperature goes up, essentially the tensile strength and the yield strength, they go down somewhat, and the ductility of a material increases. This is basically percentage reduction in area, or in other words, you could refer to it as ductility of your material. So the tempering temperature basically, if it is increased, it would provide more ductility to the material at the expense of tensile strength and yield strength. And how is the structure? Structure is such that after tempering, in martensite you have needles, you have lath-like or needles of Fe3C, which are there in the structure, sharp needles. But once you tempered it, the Fe3C particles, they acquire very fine spherical shape or very fine particles that get dispersed in the ferrite matrix. This is the structure of tempered martensite. And if we again look at the properties, with tempering, tensile strength and yield strength decreases, but the percentage reduction in area, or in other words, ductility of the material, essentially increases. Now, if we look at the effect of weight percent of carbon on the mechanical properties, we first classify materials into hypoeutectoid, which is carbon having less than 0.76 weight percent. In this, you would have perlite and ferrite. Hardness of perlite is mediocre. Ferrite is relatively soft. And in hypereutectoid materials, which is carbon composition greater than 0.76, you essentially have perlite, again mediocre hardness, along with cementite, which is relatively harder. So if you compare the three hardnesses, cementite has the highest hardness, followed by perlite, followed by alpha, which is ferrite. So now if we see, cementite is increasing as my percentage carbon is increasing. So what do I expect? Expectation is that the tensile strength, yield strength, and hardness, all the three properties, as the percentage of carbon is increasing, or as I am moving from hypo to hypereutectoid steels, the tensile strength is increasing, the yield strength is increasing, and the hardness of the material is increasing. And the ductility or percentage elongation would have exactly opposite trend. As you move from hypo to hyper, you would see that the impact energy or the toughness of the material and the percentage elongation, which is ductility, with the increase in percentage carbon, they are decreasing. So with more weight percent carbon, you have high tensile strength and yield strength, and percentage elongation or ductility gets compromised.
सर सर इससे लास्ट लास्ट साइड में फिर जब उससे कार्बन निकलता है तो फिर भी वो सर उसकी ब्रिटलनेस कम होती है ना
जी सॉरी
सर जब मार्टन साइड से सर वो जो लास्ट स्लाइड में हमने पढ़ा है उससे जब वो क्योंकि उसमें कार्बन की परसेंटेज काफी ज्यादा होती है तो जब उसमें से कार्बन निकलती है तो फिर वो सर उसकी ब्रिटलनेस खत्म होती है ना सर कम होती है
खत्म नहीं होती। देखिए
सर
मैं अभी
कम होती है
आपको
मतलब
रैंक भी करूँगा, कम होती है। मैं जब इन
सर
मटेरियल्स को रैंक करूंगा ना, इन फेजेस को, तो आपको आइडिया हो जाएगा कि कौन सा ज्यादा हार्ड है, कौन सा कम हार्ड है, कौन सा ज्यादा डक्टाइल है, कौन सा कम डक्टाइल है। आई विल गो थ्रू ऑल ऑफ दीज फेजेस, सबके बारे में आपको बताऊंगा।
ओके सर
काम के मार्टिन साइड के मुकाबले में, लेकिन बाकियों के मुकाबले में फिर भी ज्यादा होती है। ये समझ अच्छा। नाउ वी आर कंपेयरिंग फाइन वर्सेस कोर्स परलाइट एंड स्फेरोडाइट। तो विद इंक्रीज इन परसेंटेज कार्बन, Brinell hardness is increasing for all the three: fine perlite, coarse perlite, and spheroidite. But if you compare the three, you would see fine perlite would have the highest hardness and spheroidite would have the lowest hardness. And ductility, with increase in percentage weight percent of carbon, spheroidite would have the highest ductility, coarse perlite would have less, and fine perlite would have the least. So hardness के मामले में fine would have the highest hardness, coarse की कम और spheroidite की उससे कम। और ductility के मामले में it is exactly the opposite. Fine would have the lowest ductility and spheroidite would have the highest ductility. फाइन परलाइट और मार्टनसाइट को अगर कंपेयर करें तो अगेन विद परसेंटेज इंक्रीज इन कार्बन दोनों की हार्डनेस इंक्रीज हो रही है, लेकिन मार्टेनसाइट हैज much higher hardness as compared to fine perlite. So that's the difference. If we summarize this, cooling austenite slowly would give you a proeutectoid phase and perlite. Moderate cooling would give you bainite, and rapid cooling would give you martensite. If you reheat martensite, you can get tempered martensite. Now, if we look at this table, this gives you the information about structures: spherodite, coarse perlite, fine perlite, bainite, tempered martensite, and martensite. The phases present almost all have alpha ferrite plus Fe3C except for martensite, which is body centered tetragonal single phase. Arrangement of phases, if you look at spherodite, relatively small Fe3C sphere-like particles in alpha matrix, coarse perlite, fine perlite, alternate layers of ferrite and Fe3C, bainite, rod-like Fe3C, elongated particles in alpha matrix, tempered martensite, very small Fe3 sphere-like particles in alpha matrix, and martensite, you have needle-shaped grains. If you talk about properties, obviously if you come from top to down, you are moving towards very hard and very ductile phase from a very soft very hard, and you're moving towards a very hard and very brittle phase from a very soft and very ductile phase. That's how the properties changes. Processing, if you talk about processing, slow cooling would give you perlite uh, in the form of layer. Moderate cooling would give you bainite in the form of Fe3C rods or needles. Martensite would come against rapid cooling. It's a diffusionless transformation. If you reheat martensite, you have tempered martensite where you have alpha and very fine particles of Fe3C. Now these phases are labeled over here: martensite, tempered martensite, bainite, fine perlite, coarse perlite, and spherodite. Generally, as you move from spherodite to martensite, your strength, tensile strength, yield strength, and hardness, all three increases. And exactly opposite trend is seen